example, in this closed path which has been shown here, both the points we'll take this first figure. Both the points O and A, you can see this is O, this is A. Okay, we get the direction anti-clockwise at the point of intersection of the vector drawn with the TOS path. This is the TOS path when we draw. Then at this point A and O, we get anti-clockwise direction at the point of intersection of the vector drawn with TOS path. So this shows anti-clockwise direction, this shows anti-clockwise. Then the net number of intersections denoted by N are plus 1. You can see plus 1 for this, plus 1, only one encirclement. That too one in anti-clockwise direction, that is why it is written plus 1. Okay, we'll take this example particular. So when we draw a vector from this point A, and we'll consider which intersects this at 2 points. Here it intersects, here it intersects. Okay, so you can see this is also traveling in clockwise direction, this is also traveling in clockwise direction. Okay, clockwise direction. Due to that, we can write the total number of encirclements are minus 2. So this represents clockwise direction first one, this represents clockwise second. So we can write total number of encirclements are minus 2, 2 in clockwise direction. Now we'll consider another closed path which will take one more figure. Okay. Now you can see the vector that has been drawn from this point A. Vector that has been drawn from this point A intersects the path at 2 points. Here it intersects, here it intersects. But if we see the direction of these two paths at these points, here it is different direction, here it is different direction. One is in anti-clockwise, one is in clockwise direction. So you can see the direction of encirclements are different. Due to that, these two encirclements cancel each other at the time of counting final number of encirclements. Okay, hence number of encirclements of point A are 0. That is why n equal to 0 has been written through point A, even though this point A is lying inside this path 2 of S. Okay. Next we'll see about analytic function and singularities. So a mathematical function is said to be analytic at a point in a plane if its value and its derivative has finite existence at that point. Okay, has finite existence at that point, then it is analytic. Okay, if at a point in a plane the value of function or its derivative is infinite, the function is said to be non-analytic at that point, and such a point is called singularity of the function. So all such points where given function is not analytic are called singularities of that function. Now we'll consider a function f of s is equal to 25 divided by s into bracket s plus 1. Then it is analytic at all points in S plane except the point of s is equal to 0 and s is equal to minus 1. Why? Because the function f of s has a value infinity at s is equal to 0 and s is equal to minus 1, which are its pole. So putting in general form, the poles of the function are its singularities. Okay, is it clear? Next we'll discuss about mapping theorem or principle of argument. The mapping theorem states that let f of s be single valued function analytic at all points in S plane except some finite number of points. These are singularities of function f of s where it is not analytic. Now we'll consider an arbitrary closed path 2 of s in S plane, that too in such a way that the function f of s is analytic at each and every point on 2 of s path. So the restriction for selection of a closed path is that it should not pass through the points that are singularities of f of s. That is, it should not pass through poles of f of s. Let p and z be the number of poles and zeros of f of s which are encircled by 2s path. That is, they are inside the path 2 of s. Then we are interested only on those which are encircled by 2s path in s plane but not in on all the poles of and zeros of f of s. So p represents number of poles of f of s encircled by 2s. Z represents number of zeros of f of s encircled by 2s. Then according to mapping theorem, the closed path tau of s in s plane can be mapped into another plane, say f plane, to get a closed path, say tau dash. Yes, mapping procedure. So we'll see the mapping procedure with this particular example. We'll consider a function f of s is equal to 10 divided by s into bracket s plus 2. So we have selected a closed path. This is a closed path in s plane in such a way that it to encircle both the poles at s is equal to 0 and s is equal to minus 2. So here is a one pole at s is equal to 0 and s is equal to minus 2. Okay, and the path will encircle those two poles. The function f of s is analytic at all points on 2 of s path selected, and p is equal to 2. How many poles are there? 2. Both the poles are encircled by 2s path selected. Now for each point on 2s path there exists a separate value of f of s as it is single valued. This value can be plotted in another plane, say f plane. This is f plane. So how? For example, we'll take s1 is equal to plus 2. So what f of s will become? 10 divided by s into bracket s plus 2. S1 is equal to plus 2. F of s, substitute s1 plus 2, you will get f of s as 10 divided by 2 into bracket 2 plus 2, which is 5 by 4, 1.25. So it can be plotted in another complex plane f plane as you can see here, 1.24 plus j, 0 denoted as s1 dash. Okay, now we'll take at s2 is equal to plus j2, say f of s is equal to 10 divided by j2 into bracket 2 plus j2. So f of s will become, so I have taken s2 is equal to plus j2 now. One more point. So f of s will become minus 1.25 minus j 1.25, which has been shown here mapped into f plane as s2 dash. s2 dash minus 1.25 minus j 1.25. Okay, so this is obtained by rationalizing f of s. Similarly, all points on 2 of s can be plotted in f plane by finding the value of f of s at all these points. So this procedure is called mapping of a point from one plane to another plane, and f of s is called mapping function. So we get a closed path 2 dash s. 2 dashes, you can see we get a closed path 2 dash s, which is 2 dash s, you can see here 2 dash s f plane in this, which is mapped locus of 2 of s in s plane. Okay, so in f plane with the help of mapping function f of s, so this has been shown here. So this has been mapped into this plane. Is it clear? 2 of s, 2 dashes, s1, s1 dash, s2, s2 dash, and the function. So this mapping theorem is actually related to this mapped locus 2 of s, 2 dash s in f plane. So now we'll see the statement of mapping theorem. It states that the mapped locus 2 dash s encircles the new origin of f plane as many times as the difference between the number of zeros and poles of f of s which are encircled by 2 of s path in s plane. So mathematically we can write n is equal to z minus b, where n is encirclements of origin of f plane by 2 dashes path, p is number of poles of f of s encircled by 2 of s path in s plane, z is number of zeros of f of s encircled by 2s path in s plane. This statement is also called principle of argument. So I'll stop here. We'll continue next to go through this.